Relations on a set. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we explored the concept of relations from a set A to a different set B, essentially looking at how elements from one group connect to elements in another group. However, as we move forward, you will notice that in mathematics, we frequently encounter situations where the starting set and the ending set are exactly the same. When the domain and the codomain are identical, we call this specific case a relation on a set. Keep this distinction in mind, as it will be the foundation for the formal definitions and examples we are about to examine. Understanding the concept. A relation, which we'll call R, is officially called a relation on a set A if it is a subset of the Cartesian product of set A with itself. To put this into simpler terms, think back to our previous lessons where we looked at relationships between two different groups, for example, linking students to their specific roll numbers. In this new concept, we aren't looking across two different groups. Instead, we are looking for a relationship between elements within the very same group, such as looking at students and identifying which of them are their classmates. If you're tasked with defining a relation on a set A, you can follow these three logical steps. First, identify the set. We begin with a single, non-empty set, which we will call A. Second, form the Cartesian product. We create a new set, written as a cross A. This set is made up of every possible ordered pair. Let's call them X and Y, where both X and Y are members of our original set A. Third. Apply a rule. We define a specific notation or a rule. We then look through our list of pairs in a cross A, and any pair, X and Y, that satisfies this specific rule becomes a member of our relation, R. Mathematically, we summarize this entire process with a simple notation. R is a subset of a cross A. Now that we've established that a relation on a set occurs when the starting and ending sets are identical, let's dive into the formal definition. In the next slide, I'll show you how this works using a real-world example involving social connections to make this process even clearer. Real-world example, social connections. Now that we have established the formal definition of a relation on a set, let's move away from abstract symbols and look at something more intuitive. To make this concept easier to grasp, let us consider a real-world scenario involving a group of friends. Imagine our scenario. Suppose we have a set, which we will call set A, containing three friends, Amit, Bina, and Clara. Now, instead of looking for a relationship between two different groups, we want to define a relation, which we'll call R. Specifically on this single set A, the rule for our relation will be the phrase is a sibling of. Let's break this down step by step so you can see how the math works. First, step 1. We define our set A as mentioned, set A equals the set containing Amit, Bina, and Clara. Next, step 2. We need to determine the Cartesian product of A with A, written as a cross A. Remember from our previous discussion that the Cartesian product is the set of all possible ordered pairs. In this context, it represents every possible pairing of the people in our group. So a cross A includes Amit paired with Amit, Amit with Bina, Amit with Clara, Bina with Amit, Bina with Bina, Bina with Clara, Clara with Amit, Clara with Bina, and finally, Clara with Clara. Now for step 3, we apply our specific rule, which is a sibling of. To make this work, let's assume a specific fact for our example. Suppose that in this group, only Amit and Bina are siblings. We look through our list of all possible pairs and pick out only those that satisfy the rule. We find that the pair Amit and Bina fits, and the pair Bina and Amit also fits. Therefore, our relation R equals the set containing the pair Amit, Bina, and the pair Bina, Amit. Because this relation R is a subset of our Cartesian product, a cross A, we can formally conclude that R is a relation on set A. This perfectly illustrates how we use a single set to create internal relationships. Mathematical example, numerical properties. Now that we have seen how this works with a real-world social example, let's move away from people and siblings and look at a more formal mathematical example using integers. This will help you see the underlying logic more clearly. Our scenario is this. Let set A be equal to the set containing the numbers 1, 2, and 3. We want to define a relation, which we'll call R. On this set A, the specific rule or condition for this relation is that for any pair of numbers, x and y, their sum, x plus y, must equal 4. Let's break this down step by step, just like we did in the previous slide. Step 1, we identify our set A, which is simply 1, 2, and 3. Step 2, we need to list all the elements of the Cartesian product. A times A, as we learned earlier, this means every possible pairing of the elements from our set with themselves. So we list them out: 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and finally 3, 3. Step 3, this is the most important part. We filter these pairs based on our condition, which is that x plus y must equal 4. Let's check them one by one. First, 1, 1, 1 plus 1 equals 2, which is not 4, so we discard it. Next, 1, 2, 1 plus 2 equals 3, not 4, so we discard that too. Then 1, 3, 1 plus 3 equals 4. This satisfies our rule, so we accept it. Moving on, 2, 1, 2 plus 1 equals 3, so we discard it. Next, 2, 2, 2 plus 2 equals 4. This works, so we accept it. Then 2, 3, 2 plus 3 equals 5, which is not 4, so we discard it. Now 3, 1, 3 plus 1 equals 4. This is a match, so we accept it. Next, 3, 2, 3 plus 2 equals 5, so we discard it. And finally, 3, 3, 3 plus 3 equals 6, which is not 4, so we discard it. After checking every possible pair, we are left with our final relation. The relation R consists of the ordered pairs 1, 3, 2, 2, and 3, 1. Notice how, as we will see in the next slide, the pair 2, 2 is perfectly valid here because both numbers belong to our original set A. Key takeaways. First, it is important to remember that a relation on a set A is essentially a special case of what we studied previously. Unlike when we looked at relations from set A to a different set B, here, the domain and the codomain are exactly the same set. This means the starting point and the ending point of our relationship are one and the same. Second, looking back at the mathematical definition we used in our examples, the relation R is always a subset of the Cartesian product of A with A. You can express this mathematically. As R is a subset of a cross A, this simply means that the relation is formed by picking only specific pairs from that large pool of all possible combinations. Finally, a crucial rule to keep in mind is that for any ordered pair within this relation, both elements must originate from that same set A. There are no outside elements allowed. Every first element and every second element in our pairs must be members of set A. Now that we have worked through our social connection example and our numerical example, let's pause and consolidate everything we have learned with some key takeaways. Keep these points in mind, because in our next slide, we will discuss some common pitfalls that students often encounter when working with these types of relations. Common mistakes. First, a very common mistake is confusing the Cartesian product of two different sets, a cross B with the Cartesian product of a set with itself, a cross A when you see the phrase relation on set A. Do not go searching for a second, separate set B. Remember what we discussed in the first few slides. In this specific case, the starting set and the ending set are identical. The set A plays both roles. It is both the source and the destination. Second, please do not assume that the range must be exactly equal to the set A. It is a common misconception to think that every single element from our original set must appear as the second element in our ordered pairs. In reality, the range is simply a subset of A, as we saw in our numerical example with the sum equaling 4. Some elements might not appear in the second position at all, and that is perfectly fine. Finally, be careful not to overlook self-pairs. In a relation on a set, pairs where the element is matched with itself, such as x, x, for instance, 2, 2, which we saw in our previous example, are completely valid. In many mathematical relations, these self-referencing pairs are not only allowed, but are often essential to the definition of the relation. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls that students often encounter when working with relations on a set. Paying attention to these will help you avoid unnecessary errors in your exams. Keep these points in mind, and you will have a much stronger grasp of how relations function within a single set.